Welcome to this explainer. Let's jump straight in, because today we are fundamentally rethinking the absolute bedrock of machine learning. As ML engineers, we spend our lives optimizing, stacking, and tweaking the perceptron. But what if the linear thresholding model we've relied on for decades is actually holding us back? Today, we're unpacking a highly compelling biophysical alternative derived by Lanzara. It's a concept known as the net shift model, and it's a thermodynamic paradigm shift that could completely redefine how we approach network architecture. Here's our roadmap for this explainer. 1. Beyond linear thresholding. 2. The rational quadratic math. 3. The native RBF advantage. 4. Receptor constants and homeostasis. 5. Thermodynamic gradient guardrails. And finally, 6. Current engineering bottlenecks.
All right, kicking things off with Section 1, Beyond Linear Thresholding.
Think about the conceptual leap we're making here. In standard neural networks, the traditional perceptron operates on highly abstract linear thresholding. It integrates inputs linearly, your standard weights times inputs plus a bias, and then passes them through a monotonic squashing function like a ReLU or a sigmoid. It effectively asks a really rigid binary question: is the total stimulus strong enough to fire? But a net shift node, it treats that integrated input entirely differently. It treats it as a biological dose. The node's output actually represents the net conformational or equilibrium change of the whole system. Instead of just asking if it should fire, it answers a highly dynamic question: where does this cumulative stimulus push our system's equilibrium? Moving right along to Section 2, the rational quadratic math. Lanzara derived this net shift equation to model the net perturbation in receptor states as a function of a binding dose. Now, at first glance, biological equations can look pretty messy, but look at how organizing the variables yields something we can actually work with. By expanding the denominator and grouping the terms by powers of the dose, we get a highly manageable, compact rational function. And these grouped constants, A, B, C, and N, they aren't just arbitrary numbers. They represent physical realities, the unperturbed resting states of high and low affinity receptor pools, and their respective binding affinities. When you mathematically integrate this function over a dose range, the manipulated numerator allows the integral to split cleanly into two closed-form parts. It's elegant, it's bounded, and it's completely physically grounded. So, here's the pivotal question. What happens if we map this dose-response equation over to the log domain? In pharmacology and biology, dose-response graphs are traditionally analyzed logarithmically. If we transform our variable to the natural log of the dose and apply a Laplace approximation around the peak response, something incredible happens. We map this rational function directly to a Gaussian profile. And that leads us to this beautiful mathematical landmark. By taking the first derivative of our log-transformed equation and setting it to 0, we find the absolute peak biological activation dose. It always occurs exactly at this formula: the square root of the high and low affinity dissociation constants, divided by 2. This defines the mean of our log-dose Gaussian distribution. What is absolutely mind-blowing for network architecture here is that this peak is entirely independent of the initial receptor quantities. It is structurally locked in by the affinities. Meanwhile, the variance, or the width of our activation window, is explicitly regulated by the ratio of those resting states combined with their asymmetric affinity weightings. Which brings us to Section 3, the native RBF advantage. Because the net shift equation is a rational quadratic, its activation profile is natively bell-shaped in the log domain. Think about traditional perceptrons for a second. They are strictly monotonic. As input goes up, activation either stays flat or goes up. If you want to model a system that turns off when a stimulus gets too high, creating a localized boundary, you literally have to chain multiple layers of perceptrons together. But with the net shift node, as the input dose approaches infinity, the quadratic term in the denominator completely dominates, and the output naturally decays right back to 0. A single node inherently acts as a built-in radial basis function. You're getting native peak optimization without needing deep, multi-layered architectures just to force a boundary. Comparing these features side by side highlights a massive leap in role flexibility. A standard perceptron node is rigid. It amplifies, dampens, or blocks based on a static synapse weight. But a net shift node features something called inverse agonism. By simply tuning its internal affinity parameters, a single node can express partial activation, baseline constitutive activity, or completely reverse its function from excitatory to inhibitory. Its role is determined by the structural state of the system, not just a static, frozen weight. Let's dive into Section 4, receptor constants and homeostasis. Imagine a highly constrained environment, a finite pool of high and low affinity receptors. This represents the strict conservation of matter. In a NetShift node, the sum of these receptor pools equals the total system pool. If a node is overstimulated, it cannot simply blow up to infinity. It automatically dampens its own output based on the finite availability of these combined receptor pools. It's a remarkably self-regulating system.
For us ML engineers, this is effectively a native batch norm layer built directly into the node's physics. Artificial neural networks constantly struggle with oversaturation and catastrophic forgetting, requiring complex normalization layers just to stay somewhat stable. But Lonzara's model structurally incorporates tachyphylaxis, which is rapid desensitization. It obeys Le Chatelier's principle for homeostatic equilibrium balancing, and because it structurally adheres to Weber's law, the node naturally processes relative changes in input rather than absolute values. This makes the network insanely resilient to background noise or shifting input scales natively.
All right, Section 5, Thermodynamic Gradient Guardrails. Exploding gradients. We've all been there, right? Numerical values growing boundlessly during deep network training, completely destroying the model. But the NetShift node operates under those strict conservation of matter constraints we just talked about. The maximum possible output of any individual neuron is mathematically capped by the physical capacity of the system. You have built-in thermodynamic guardrails at the individual neuron level. The math simply will not allow the gradient to explode beyond the physical receptor limits. So if this is all so mathematically sound, why aren't we all using it? And that brings us to Section 6, Current Engineering Bottlenecks. Here are the brutal engineering truths. Modern hardware is tailor-made for simple linear math. The first massive hurdle is computational overhead. Think about a ReLU activation. It's computationally virtually free, literally just taking the max of 0 or x. That's exactly why we can train billions of them in parallel. Evaluating a rational quadratic function with multiple parameters at every single node, on the other hand, drastically slows down forward and backward passes on standard GPUs. Then we have the optimization complexity. That beautiful bell-shaped curve that makes this node so mathematically powerful, well, it's a double-edged sword. It creates two-sided saturation. If the initial weights accidentally place the input dose too far to the left or the right of the peak, the gradient drops to near zero. And as we know, when gradients drop to zero, standard backpropagation stalls out completely, and the network starves. Which leaves us with this final, incredibly provocative thought. Yes, running this on traditional GPUs with standard backprop is a bottleneck today. But think about the sheer theoretical power we just unpacked. If a single NetShift node armed with native RBF, built-in homeostasis, and dynamic inverse agonism can replace massive, deeply layered perceptron architectures, is this the key to the future of small footprint edge AI? As we eventually transition away from traditional silicon toward neuromorphic hardware designed to actually mimic biophysics, the NetShift paradigm might just be the exact foundation we've been looking for.